Last lesson we talked about exponential growth, and today we're going to contrast that with exponential decay. But the key idea before we get started is that in both cases, we are still using this equation where we take some initial value, A, and then we multiply it by some growth factor, B, a whole bunch of times. And that x, that exponent, is only telling us how many times are we multiplying it by, because that's what an exponent does. Right, so whether it's exponential growth or exponential decay, it's the same equation. And the only difference is that in exponential growth, you're going to be multiplying by a number bigger than 1, like 2 times 2 times 2 times 2. As you multiply by 2, you're going to keep getting a bigger number. You're going to keep growing. In exponential decay, that number b is going to be less than 1, let's say a half. As you multiply by a half, you're going to keep getting a smaller number. So now let's look at these two examples and we'll see how they differ and how they are alike. Okay, the one on the left, let's look at the chart. So notice as we keep adding 1 to x plus 1 plus 1, we are not adding here because that wouldn't work for both. We are multiplying. So times 2, and so to complete this chart, we know that's times 2 again, 16. Times 2 again is 32. And we can graph this, right? So when x is 0, y is 2. So right there. When x is 1, y is 4. Right there. When x is 2, y is 8. So 2, we're going up to 8 now. 3 is 16. We're going all the way up to 16. And then 4 is 32. And that's all the way up here. And so you can see this curve. Remember, exponential growth is shown on a curve, not a straight line. You can see how rapidly that increases, okay? So that is exponential growth. And what was the driver there was we were multiplying by 2. That was B, right? So in this case, let's just write out the things, right? A was 2 because we were starting there. But B was also 2. B is the number we're multiplying by. And then x is just however many times you multiply it by, right? So this was after we multiplied it by 2 once, twice, 3 times, 4 times, and it's just going to keep getting bigger and bigger. Now, exponential decay, we're still doing the same thing here. X is just going plus 1, right? But look at what's happening to the y. We went from 2 to 1. Well, that looks like division, right? Because then we went from 1 to 1/2. We're getting 1 is half of 2. Half is half of 1. So we could think about that as dividing by 2, but notice in our equation we're multiplying. So we can think of dividing by 2 as the same as multiplying times 1/2, times 1/2. And so if we did that again times 1/2, we would get a quarter. Think about that. If you had half of an orange and you split that into 2, you'd have 2 quarters. And if we multiply it by 1/2 again, we would have 1/8. If you split that quarter of an orange into 2 pieces, each of those would be 1/8 of the orange. So now we can graph that. When x is 0, y was 2. So we have the same starting point. Notice that we started at the same point. We started at 2. But in this case, when x was 1, y came down. We are only at 1 now. When x is 2, we're all the way down to 1/2. When x is 3, we're at half of that. That's a quarter. And then notice we're getting closer and closer to that x-axis. But again, it's not a straight line. That's a curve. So that is just like exponential growth. The difference, though, is we're going down. Exponential decay means our values are getting smaller and smaller. And it's driven by this b of less than 1, right? So in this case, A was still 2, same starting point, but B was 1/2. We were multiplying by 1/2 a whole bunch of times. And that's all x tells us, right? Is how many times we're multiplying by 1/2. So in the real world, where are examples of this? Well, exponential growth, we could see it now with the coronavirus expanding across the world and our country. But human population is another great example of exponential growth. You can see here in 1700, even 1800, we were still, 1800 is maybe right there. We're still below 1 billion people, right? 1900, we're like maybe then we've just gone above 1 billion people. But look, just in this last 100 years, we've gone from about 1.5 billion or something all the way up to, we are right about here right now, about 7.7 billion people. So you can see how quickly that the human population on this planet has grown in just the last 100 years, and that's an example of exponential growth. Again, that's a curve. You can see the curve there. It's not a linear growth. It's not a line. Exponential decay, a common example, is with the half-lives of radioactive material. And you can see here, over time, as time goes on, the radioactivity of that material comes down. But for a lot of them, it takes a long time, and that's why we're super cautious with radioactive material. All right, moving on. So the other day we looked at the exponential growth model for like an investment, right? And the same thing's gonna be true today. We're gonna look at it again with decay. But two key things before we go. The first is that it's just the same thing as our other equation, right? Nothing is different. A is still the initial amount. X, in this case, T, because it's time, is just how many time periods, right? How many times are we going to be multiplying the growth rate? The only difference is we're just, instead of B, right, we're calling it 1 plus R. But that's really just B. Same thing here. 1 minus R is B, okay? And the only other difference is that exponential growth, remember, we're multiplying by a number bigger than 1. Exponential decay, we're multiplying by a number less than 1. Same idea, and we're just applying it to, we're looking at it in a different way, and you'll see how that is, right? Okay, so the first example, you invest $500 in a stock account with an average rate of return of 6% per year. How much money will you have in your account 8 years from now? How much money did you make? Okay, initial amount, A, is $500. Okay, that's where you're starting. What is your rate of return? 6%. So R is 6%, right? But how are we going to write that? 6% is 6 cents, right? So you can just write that like that. And then 1 plus R is just $1.06. So that's pretty simple. And then T is just the time. How many times are we multiplying by 1.06? And it says 8 years, so T is just 8. So now all we have to do is plug in that information. So we have our amount is equal to 500 times 1.06, and we're multiplying that 8 times. Remember, if we wrote that out, it would say 500 times 1.06 times 1.06 times 1, right? 8 times, because each year we're multiplying that amount we had before by the 1.06. So let's just do that. So we have 1.06 to the 8th power, and we multiply that by our 500, and we get $796.92. And notice it grew because our B, our growth factor, was bigger than 1. 1.06, even though it's close to 1, is still bigger than 1. Now let's look at an exponential decay example. Since 1963, the number of acres of ponderosa pine forest decreased. Look, we're going down. Decreased in the western United States by about 0.5% annually. So now we're going to take a close look at that number. How are we going to write that as a decimal? In 1963, there were 41 million acres. About how many acres are left today? Okay, so A, right, where are we starting? 41 million acres, right? That's where it was, 41 million acres. Okay. Now this R, right, is 0.5%. Now remember, when we did it over here, right, 6% became 0.06. When you're taking percents, you're just moving the decimal place to the left 2 places, right? If we took 6 and we move it to the left 2 places, we get 0.06. So all we have to do here is move it to the left 2 places, and I'll just change the color real quick. So it's going to go like that, and then so you're going to end up with 0.005. Okay? Now, in this case, 1 minus R, right? So 1 minus R is just going to be 1 minus 0.005. So now, notice we're not going to be decreasing too rapidly, but we are still decreasing. So that's going to end up with 0.995. Okay? So that is our B. And then T, we also have to figure this out. So we started in 1963. So we just have to figure out how many years have we been doing this since. Well, we're in 2020. So 2020 minus 1963. So 2020 minus 1963, right, is 57 years. So 57 years, and that'll be our T. So now let's just plug in what we've got. So we've got 41 million. So 41 million times 0.995. So we're decreasing a little bit every year, but we've been doing it for 57 years. So I'm going to do 0.995 to the 57th power, because I'm multiplying that by itself 57 times, and I'm multiplying that by 41 million, and I'm getting 30.8 million. 10550, and that is acres. So you can see, even though we were only going down a tiny bit each year, 0.5%, we lost a little more than 10 million acres, right? We went from 41, we started, and now we're at 30.8 or about 31. So we lost about 10 million acres of ponderosa pine land, and that's a relatively short amount of time. You think of, the world's evolution over millions of years. And so just in 57 years, we've lost 10 million acres of that pine forest. It's quite a bit.